Okay. Let's do this. There's a lot of slides in this one, but there's a lot of pictures, so hopefully it won't take all that long. This is about part 2, routing and switching, and this is advanced switching techniques. I think that's what they call it, enhanced switched technologies. What we're really talking about, we talked about switches and we hooked stuff up to them. You remember it took 50 seconds while spanning tree configured the port. What spanning tree is looking for to see if there's an actual loop. What this is about, most of the chapter, well, all the chapter really, is spanning tree. At the end, we'll learn how to, and one of the things that you probably thought about when we do that, when we have duplicate links, is like, there's one sitting there doing nothing because it stays amber. We're going to learn at the end the process called ether channel, where we bind 2 ports together so that they both can be working. So what it really means that if you have 2 gigabit ports and you bind them together, instead of a gigabit connection, you've got a 2 gigabit connection. Or if you put 100, I think it's up to 100 meg ports together, put 8 of them together, instead of 100 meg, you've got 800 megabytes of transfer. Huh? Full duplex. No, it's going to be full duplex, and they all have to be the same. I mean, you can't put a gigabit in a fast Ethernet together. Those sorts of things have to be full duplex. Switches are full duplex. When you think switch, think full duplex all the time. When you think hub, think half duplex. So the spanning tree protocol, what it does is we achieve our primary objective, I'm going to do this thing, of preventing loops on layer 2. Remember layer 3, we had a hop count, so they would die. Layer 2, we don't have any of that stuff. So if we get a switch here, and switches forward all broadcasts, right? That's what they do. So if we have 2 things, and this would work better with 3 switches, but we'll just do 2 here. It gets a broadcast, it forwards it out all of the ports. And this one gets a broadcast, and it forwards it out all the ports, and it just starts building as it goes around in a circle. Building and building and building until eventually your whole network goes down. Trust me, that works. I think I told you the story. A student, one of the night classes on our work days, created a loop, and this was actually a hub, but took a hub and plugged a wire in to 2 ports. Plugged the wire in this way. Well, you've created a loop here. So he created a broadcast storm on the entire network because it wasn't subnet. Advantage of subnets is if you have a broadcast storm on a VLAN or a subnet, then that broadcast storm only affects that VLAN or that subnet. But he had brought down the entire network. When I got to work, the network administrator was feverishly trying to fix the routers. He said he thought a router had died. I went in, would happen to be in my room. Went in there and saw this device with all of the lights just bright because of the broadcast storm. Unplugged the loop, and it started fixing itself slowly. It doesn't do it instantaneously, but after about 15 or 20 minutes, it was back. So the spanning tree protocol can really save you. And I think I probably one more story. Told you about the guy that was in Roanoke that got called back to a job that he'd done in Chicago. Flew in from Roanoke to Chicago, paid him that per diem and the consulting fee and all that stuff. He walked into the network operations center and moved 1 wire and put the network back because they had elected not to use the spanning tree protocol. And somebody had moved a wire from one port to the other, and he knew where they were all supposed to be. He moved it back, fixed the network, got his fee, and went home. So it's not always what you do, and in this world, it's really kind of observing and what you know, not what you necessarily do. It uses the spanning tree algorithm, and that's something that you just need to know. It uses the spanning tree algorithm to create a topology database. And when we talked about OSPF had a topology database. So it's going to create this database, and then it's going to look for redundant links. If we take our 3 guys here, if we hook them all together, we have a loop so that we can get a broadcast storm. What spanning tree is going to do, and it's going to be based on this algorithm down here, and we'll just pick this one, it's going to block one port so that it breaks the loop. Advantage here is if one of these links goes down, it keeps getting BPDUs, the Bridge Protocol Data Units, and says, oh, something happened, we need to check again. Oh, I'm not a loop anymore, I need to activate, so it can activate itself. So you can have some self-healing here if you have failures in ports. Somebody pulls a wire out, trips over a wire, things like that, because that happens. Frames, it says frames will be forwarded only on premium STP chosen links. And I think, and that's true, but it actually is more likely that they won't be forwarded on chosen links, the ones that are going to be called what we'll call redundant links. So switch network with switching loops, we've talked about that. With redundant topology, the 3 that we just showed, there is nothing blocking this. So when we get our broadcast here, and it probably works better here, broadcast goes out all ports, right? Gets to this one, the broadcast goes out all ports. Gets to this one, and the broadcast goes out all ports. Well, now it's on all the switches again, so it's going to do that again and again and again and again and again. Eventually, it will overwhelm the switch, and it won't be able to do anything. Multiple frame copies. MAC table thrashing. What MAC table thrashing means is that first it gets the broadcast from a computer, and it says it came in this port, so it puts that one into the MAC table. And then it goes around and it comes into this port, and then it puts that port into the table, and then it goes back to the other one, back and forth, so that the thrashing around the MAC table, thrashing in these things. So this is against the same picture, no loop. This is one that actually does have the loop in it. Actually, this is the one, the no loop. These are the ones that have the ports closed. It can be a complex, it can be the 3. The 3 is easier to see, but if you have a big network, spanning tree will automatically block, and blocking is the term that they use, not shut down, but block. Shutdown is when you give the no shutdown command, but block the ports to create single paths. What we sometimes need to do is manage which of these, the root bridge is the one that everything's going to go through one of the bridges, and it looks like, if I were guessing, I guess this one is going to be what we would call the root bridge, so, because it's got everything connected to it. The problem when we get into it and we talk about the process that it uses, all things being equal, it's going to use the bridge with the lowest MAC address, which means it's going to use the oldest bridge or switch, because MAC addresses increase as we go through this thing, which means that then the most important switch is going to be the least capable one in most cases. That's why you really need to know how to manage spanning trees, so that you can call the tune and dictate which of the switches is going to be the root bridge. So terms here, and I've already talked about root bridge, is a bridge with the lowest bridge ID. I said MAC address. We also, and we'll, if you look down here we have the actual what it is. We have the MAC address, 6 bytes, and then we have the bridge priority is 0 to 65,538. All of these things are, I think it's, well, I just want to hear them. I think it's 37,628. They all start out with the same number. So if they all have the same bridge priority, then the MAC address is going to be the one that dictates which one is going to be the root bridge, and you always use the lowest. So if we were going to change the bridge priority and we wanted something to be, and we can do that with the commands, if we're going to change the bridge priority, we're going to make it lower to force that other switch into being the root bridge when we do these things. The reason that the bridge priority works so well is it is here in the most significant bit portion of this thing. So if we could lower this any at all from the 37,628, and again, I think that's the right number. If we lower it at all, then it's going to have priority because of where it is. It's like having a really big number like this, that they're all the same. But if we change one bit up here, make this a 1, then it's going to be the biggest number. So if we lower this at all, since it's at the front end, these things all combine to be a single number. So any change in the bridge priority to lower it is going to make that bridge the root bridge. The non-root bridges, that's everything else. So we actually have one root bridge in a network. The BPDU bridge protocol data units are used to exchange the information, including the bridge IDs used for the root bridge election. So this thing does bridge IDs, and the bridge ID is the combination of the priority and the MAC address that we see down here. And again, by default, they all have the same bridge priority. So the MAC address, and it's going to be the lowest MAC, is the one that will be the root bridge, the really big deal bridge. Spanning tree terms, port cost is a value to determine the best path if we have multiple links. And what that means is that if we have something like this, and we're going to determine the path to the route wherever it is, we're going to have costs associated with these based on speed. And as I recall, we have things like the gigabit that costs 19, 100 meg, and I've got a table here, and there's a table in the book. I think 100 meg is 19, cost of 19. So if these were 100 megs, 19, and maybe we have a gigabit, and a gigabit would be 4, 10 gigabits too, I think. So on these things, the 4 obviously is going to be, it doesn't really work well here, does it? The 4 is going to be the lowest cost. Any other way, we're going to have the 19. It's going to be the same cost for these things. But, well, actually, let's make this one a 4 and this one a 19. Instead of going directly here with the 19, the more efficient path is actually the longer path, because it's going to be 8 versus 19. So it should choose, and this is all happens automatically, should choose the low cost path when we do these things. The path cost is the value used to calculate. So what we have here are the port costs, and the port costs are based on the speed. The gigabit is 4, and the 10 meg is 100, I believe, and the 10 gig is 2 when you're doing the cost. This one down here shows spanning tree. It tells us about it. What this says 32,769, and the reason is it's VLAN 1. We're going to see why this is in a minute. When we get into VLANs, we add another factor in here for the ID, and what it basically does is adds the VLAN number to the priority, the 32,768 plus 1 gives us a 32,769. It tells us what the MAC address is, and it says this bridge is root. It will tell us if it is the root bridge. It's also going to tell us how it would get to the root bridge, so that you can actually go find the root bridge by doing a show spanning tree and then using show CDP neighbors to find out where it is. And if you're using a packet tracer or something like that, all you got to just look at it. So it's going out that port. Well, it's got to be the next bridge, the next switch. So those things can be found. And then we have the ports on this thing, the root bridge. All the ports, and we haven't talked, we're going to get to those terms in a minute, but they're all going to be forwarding ports, which means that they're all active ports. None of them are blocked. There are no blocked ports on a root bridge. So this shows all of those things. This is one I just thought was kind of interesting. The root port, each of the, and this one, the red ones here are the root port. The root port is the one connected in the path that goes toward the root bridge. And I was just looking at this thing. I think this one up here at the top is the, this one up here at the top is going to be the root, I believe. Does anybody see it? Does anybody see that it says it's the root? We're going to assume it is. I think this one was the root on this thing. So all of these things, the root bridge goes to a forwarding bridge, and the ones that root ports connect to are going to be called designated ports. So we have a red one here, which is a root connected to a green one. A root connects to a designated. Over here we have a root port connected to a designated port, and then it's going to go this way. So this one's path is this direction, and these are gigabit connections here. I think we got fast Ethernet gigabits here, and as we go through these things, and we got 32,778 on each of these, and that doesn't matter. So I guess we could look at the MAC addresses, couldn't we? 17, I don't see anything, so that is the root. They all got the same priority, 32,778 it looks like. So the lowest MAC, the 00, and the way you do this, just go to the first bit and go around. Got a 0 here. Got a 5 here. Well, that one's out of the running. Got a 0 here, still in the running. Got a 0 here, still in the running. Go to the next one, got a 0. Got a 0, got a 0. 1, got a 2. Well, that throws that one out. Got a 1. So we still have 1s. Go to the next one. This one has a 7, and the one on the left's got an A, and the 7's the lowest. So this guy here will be our root bridge. All of the ports are green here. Are forwarding ports. They're designated. Designated is the spanning tree term for the forwarding ports, which means that they're active. The root port is the one that is the outgoing path to the root bridge when we do these things. The non-designated port here is going to be blocking. So it's going to not be forwarding data. If one of these goes down, it can come up and become a forwarding port. It would be a root port on this guy. Over here we have the duplicate the loop of these two things, and it's Fast Ethernet 1023 and Fast Ethernet 1024. You notice that 23, if I can get over here with this thing, 23 is the forwarding port, the root port, and 24 here is a non-designated port, the one that is blocked. If you get down to ports, the lower port wins. So when we're talking about these things, to find the root bridge and to find the path, everything is the lowest, which on the port's not a big deal, but on the switches themselves, the lowest is probably going to be the oldest, which is going to be the least capable. So what we're going to do to call the tune, so to speak, is to change the priority to something that will lower it on the one that we want to be the root bridge and force it into being the root bridge. So the root port's the link with the lowest cost path to the root bridge. It's on the non-root bridges, and we have one per bridge, and it connects. The root ports connect to designated ports. All root ports are all ports on the root bridge are designated ports, and the ports in the forwarding mode are the not root bridges. When we talk about these things, we're also going to be able to connect devices on access ports. And before we go too far and you get the idea, well, this is it. These are going to be trunk ports. These are going to be trunk ports so that they're actually carrying data from one switch to another switch across the network. We're going to have devices here on access ports that are going to be connected to it, and they're the ones that obviously put their information on the trunk ports to get from one location to the other. And the non-designated ports are the block ports, the yellow ones here. And that's what makes it a non-looped system, are the block ports. Forwarding ports, a root or designated port. Block port does not forward frames, but it listens to the BPDUs, the Bridge Protocol Data Units. That's so that if we have a change, it can determine, am I needed? And if it's needed, then it will go from a block state to a forwarding state. And then an alternate port is in the blocking state. Alternate ports are kind of, to me, ill-defined, but they're really in the 802.1W, which is the rapid spanning tree. It's a different protocol. The one that we're using right now, that we're talking about, spanning tree, is 802.1D. And then we have backup ports, and backup ports, again, it says on both of these, but it's really an 802.1W term. The switch with the highest bid becomes root, and the redundant paths will be blocked to prevent the root. The highest bid, maybe we should say the best bid, best and not highest, because we know that it's actually the lowest priority that is actually going to become the root bridge. The port states disabled means that we do that with the shutdown command. Blocking is just listening. All of them start this way. They start as blocked ports. And then after, in the timing sequence, they go into listening. And all they do here is listens to be sure that there are no loops. If there are loops, then spanning tree is going to keep some of them in blocking mode. It prepares to forward frames, and it does not populate the MAC table at this point. After we go from listening, after listening it goes to learning. It listens and learns all the paths, and at this point it populates the MAC table. After spanning tree is convinced that there are no loops, the learning ports that have progressed then go into forwarding mode. Once the optimal path is discovered, the redundant ports are blocked. They're actually never unblocked. And that's what we want. And this is just a table, the same thing, forwarding, sending, receiving user data. So these are the ones that are actually sending data. Learning is building the bridging table, the MAC table, and the no loop table. Listening is building the active topology, and the active topology is going to be the one with no loop. Blocking receives PDUs in case something changes, the topology changes. Then it may become one of the ports that are required. And then we have administratively down that when we use the shutdown command to do those.
Hold on, can you go back to one?
Yeah. The blocking, the forwarding, learning. And this is the prior, and when we do this, actually we'll go this way. When we go this way with 802.1D, it takes roughly, and I think you'll see that, 50 seconds, 50, almost a minute. And you've seen that in Packet Tracer when we plug something in, you sit there and you wait and you wait and you wait. Not necessarily good. And I think I told a story about, we had that in the classroom. People come in and the computers would start up automatically in the morning. And they would come in and hit space bar and try to log in. And when they hit space bar, that would activate the NIC, which was plugged into a port. And that port would then initiate the spanning tree, this process, and it took a minute. Well, they would go ahead and type in their username and password. Takes less than a minute to do that. And they get an error message back that said that there are no authenticating servers available, which means that you can't get logged in if you don't have any authenticating servers. So we're going to get to the process here in a minute. What we did was configure these ports with a process called PortFast. If you're only going to have computers on these things, you don't really need to check for loops because you're only going to plug in one device, an end device. And there's a process called PortFast that we'll do, and it's in the lab activities to do, where when you plug in, it automatically comes on. So this is back to when we want to do these things. I think in the book he says, what if you need a DHCP address? You plug it on, you're not going to get a DHCP. You're going to get a 169, a PIPA address, because it couldn't get the address. The machine's ready to go, computer's ready to go, port's not ready to go if we just use the standard 802.1d to take the 50 seconds for these things to come up. Convergence is when all ports are either blocking or forwarding. That means that they all have the same topology. They're all singing from the same tune. When we talk about routers, when they're in convergence, they all have the same routes. They all have the same route tables. When we're talking about Active Directory, when they're in convergence, they all have the same information. This is something here, when convergence is in progress, all data transfer stops, because if we go back to this process, blocking, listening, learning, and then we go into forwarding, takes the 50 seconds. We have to get to forwarding mode before data is actually transferred. The link costs, the 10 megabits, 100, and I think this table's in your book. 100 megabits, and maybe where I got it. 100 megabits is 19, a gigabit's 4, and a 10 gig is 2. And this is the one where we find the most efficient path to the location. So these are actually, these slides were mixed, some of them from from Lamley and some from the company here. So we're going to summarize what we've learned so far with a simple 3-switch connection. When we look at these things, the priorities, and these are all the priorities are 32,768, which means that we're going to go to the MAC address to determine the root bridge, and this one tells you the root bridge. When we look at it, this one is all zeros in an A, so that's not going to be it. And all zeros are 003, so this one is going to be the root bridge. The paths, these are all gigabits, so the cost for each of these is going to be 4, and this is just a number. It's not $4, not 4 anything, it's a number. So it's going to be looking for the lowest cost. So we got a 4 here and a 4 here, and now we're connected, but we still have our loop. Not even these things are not going to go in these directions because the cost would be 8. So one of these two is going to be the block port, and let's see if I can guess right. Which one do you think it's going to be? This was a 000A and a 00003. I think probably going to be this one because it's the highest. This is the lowest MAC. And we got root port, I think he's going to tell me, and eventually we have the root ports. The cost is 4. Remember, the root port is the one that goes to the root bridge, or in the direction of the root bridge, and here they're connected. And it connects to a forwarding port, and it's going to be called a designated port. Designated port. So a root port goes to a forwarding port, designated port. And all these costs are 4. So after they agree on the root bridge, they got to then determine the one and only root port on the individual switches. Good guess, right? So here we got the one with the lowest MAC is the one that's going to be, and this is going to be a blocked port. It's not going to be down, it's going to be blocked by spanning tree. So we have our root ports going to the forwarding ports, which are actually in spanning tree terms designated ports. This one's going to be a forwarding port. It's going to be up. It's going to be live, so that if something happens in the topology, this link goes down. This port can then go from block state to forwarding state, and this switch still has a path to the root bridge. Again, the root bridge, if the priorities are all the same, and they are here, we're going to use the lowest MAC address. Maybe not the best thing, because the lowest MAC address is probably going to be the oldest switch that you have. S1, this is same process, the 32768. Actually, it's the same one, isn't it? So in this one, all zeros. This is going to be the root bridge. The lower MAC over here, the higher MAC address is going to be blocked. These are going to be root ports because they go to the root bridge. These are going to be forwarding ports, which are called in spanning tree designated ports. And this will be a forwarding port. A forwarding port just means that it's up and ready to send data. It's going to be green when you look at the lights. The block port's going to be amber. Yeah, it's the same. The bridge priority, we've kind of looked at this already. The bridge ID is the first 2 bytes, or the bridge priority. The bridge ID, and we'll call it the bridge because then we'll have to write out all this stuff. We have the MAC address and the bridge ID. When we put these two binary or hexadecimal numbers together, we get the whole string. The reason you typically are going to say that it uses the lowest MAC is the bridge priorities are the same, 32768, by default on all of these things. So when we use it along with the MAC address is going to be the only thing that changes. We can change the bridge priority if we lower it at all, since it's out here at the front end, it's the biggest part of the number. That bridge will then become the root bridge. The types of spanning tree, the 802.1d is the original, slow, and on it all VLANs have the same root path. PVST is per VLAN spanning tree, and this is the Cisco default, which means that when we have VLANs, each of them can have its own root bridge. They don't all have to follow the same path. Rapid spanning tree has faster convergence, takes more resources. It is the same as the original spanning tree. Is you have one root bridge. Again, Cisco has per VLAN spanning tree, rapid per VLAN spanning tree, which means that, again, each VLAN can have its own root. And 802.1w, rapid spanning tree, and I've forgotten the exact command. I may have it here in a minute, but you can turn on rapid spanning tree. It's not the default. Per VLAN, PVST, plus here is the Cisco default for their switches. And if you do rapid, all of the switches have to have it to support it before it's actually going to work for you. This is the common one, and in this one they all have the same root bridge, which means that we have servers here for management, engineering, and CAD, and servers here for sales, finance, and marketing. So we have CAD, marketing, engineering, finance, and management here. All of these guys, and in here somewhere, we're obviously going to have block ports in this mess. And spanning tree will calculate that for you. And if we didn't do anything else, this is going to be the lowest MAC, which will be the oldest switch, which may not be what you want in your network. But on these, everything is going to have a path to the root bridge, including these guys over here are going to have to get to the root before they can come back to their servers. But this is one of the handicaps that you have if you only have one root bridge. The per VLAN spanning tree on this one, we have a root bridge. We can have different root bridges. This is for management, engineering, and CAD. So management and engineering and CAD here spread out, but they go here. Not everything goes to the same location, and the other departments here, this is going to be the root bridge for them. Again, we can manage these by changing the priority in the spanning tree system. The per VLAN, and this is what the BPDU is going to look like. Remember, we had what, 2 bytes, right, on this thing, and 6 bytes for the mat. 2 bytes is 16 bits, right? So we have here 16 bits, the bridge priority. The sys ID in here, extension, is actually going to be the VLAN number. So it's going to associate it with a VLAN. And what will happen here is we have what, 32,768. If we had VLAN 1, the priority is going to wind up being 32,769. VLAN 2, 32,770, those things. So they will automatically kind of change the priority, but we can do those things to manage them, and we can have a different root bridge for each of these guys. The rapid spanning tree on this one, this has got the 802.1d, the old spanning tree, we'll just call that STP, and this be rapid spanning tree protocol. Discarding, discarding, discarding. You notice that disabled, it doesn't do those things. It goes directly from discarding to learning to forwarding. And learning is when it's learning about, it actually starts populating the MAC table. And then it goes into forwarding. When it goes into forwarding, it should have its MAC table already populated. The links here, I'll just put this table in here, the 10 meg, 100, 100 meg, 19, the link cost. We got gigabit here, so this will be a 4, a fast Ethernet here. These would be cost of 19, a gigabit here would be 4, and a gigabit here would be 4. Notice that this one, see which one's our root. It looks like this is going to be the root here, right? Because it's all zeros. And we're going to make the assumption that they're all the same root, the priority, because it doesn't tell us anything different. The path for this one, the fastest path will be this way. So this will be the root bridge. This will be the forwarding bridge, or the designated port, the designated port, the root port, the designated port. I'm going to call them designated because that's what spanning tree calls it. This will be a designated port, a root port, 21, 1B, 1C. So 1C is going to be the higher number. You could just go one at a time till you find a higher number. And that one should be the block port. So this one will still be forwarding. If anything goes down, it can go this path. It doesn't even use this connection here unless something happens to it. Hey, good job. We figured that one out, right? Root, I should have slowed down. The cost, actually, I thought that one was, this is, wow. Well, what this is, and this is a fast, this, it doesn't say, but this is going to by fast Ethernet 0 whatever. We'll say 02. If it does, even though this is a gigabit port, it's going to be degraded to fast Ethernet speed because you can only go as fast as the slowest link.
Okay.
So each of these would be a 19. Yeah, this one says a gig 0, and it's a gigabit port. But this one's a fast Ethernet port. When we connect a gig to a fast Ethernet, it becomes a 100 megabit connection. Because this one can't go a gigabit speed because it.
Well, even if you're driving a Lamborghini, if you got no gas, you're going.
That's right. If you get behind a Yugo, you're going to go as fast as a Yugo, right? In that Lamborghini. So this one, which one is going to be our root bridge? And this one, let's look at the priorities. I'm going to walk you through this. This one's 28,672. The rest of them are defaults. This is substantially lower than anything else.
Mm-hmm.
So this one, the lowest is going to be the root, I believe. And they always got the answers, and you can see if I lied to you. A 10 gig is going to be a cost of 2. All of these gigabits are going to be a cost of 4. And these are costs that you can look up. You used to have to remember like 3 tables. Now you only have to remember the one table. The 10 was 100, right? The 10 meg. It's going to be unusual to see a 10 meg connection. The 100 meg was 19. The 1 gig was 4, and the 10 gig is 2. So when we do these things, this is going to be the root. So we have to find the best path for each of these guys to the root bridge. Let's see if we can do that. And this one's a little more complicated than the others are. Agreed? There's a lot more redundancy here, and we could throw another one in here. But this one's pretty obvious because if we go this way, it's going to be 6. If we go this way, it's going to be 4. So let's see if this is the root bridge. This will be a root port. This will be the designated port. This one's a 10 gig. No question about this one, right? We think. When you think that's going to be this one, this should be the root because this path is 6, this path is 4, and this one's going to be a designated path. So now we've got to figure out here which one of these are going to be enabled. And I think this is the one that we have normally gone with the lowest MAC address. But in this case, if we made this one the block port, the port cost here is 8. If we make this one the block, the port cost is 6. And keep in mind that there may be connections on this segment. We just showed these things together, but there may be connections on, maybe something attached on this segment. So I think this one, and we've got the answers here in a minute. We'll find out here in a second.
Why wouldn't SB be the block port?
Well, which?
That one right there.
This one?
Yeah.
It should be.
Oh.
SB.
Oh, okay.
Because we have a 6 here, and we have a 4 here, right? So I mean we're finding the best path,
Mm-hmm.
and I think this one should be the blocked port here because it's going to have a higher cost. If we go through here, even though it's a 10 gig here, it's going to be a cost of 6, and this is going to be a cost of 4. So let's see how do we do? Root port, root port, root port. Those are the ones that we picked, right? And then we got to go which one are going to be the blocked ports. And we got those right too because this is going to be the cost. The others I think had the same speed. They were all like gigabits and 100 meg connections. But what is the best path to these things? We got the root. This one's going to be blocked because it has obviously a higher cost. And the kit 10 gig, 1 gig, again for the cost, the 1 to 2, or the 4, and the 4, and the 4. To modify these things, we can show the spanning tree VLAN 1, which is going to show us, and I've got some, and they're in the hands-on lab, the activities do that. We can show the spanning tree. We can change spanning tree priority 16,384. Once we do per VLAN spanning tree, they have to be in increments of 4096. The reason is, if we go back to this guy, we have 12 bits here, and if you'll go 2, 4, 8, 16, 32, 64, 128, 256, 5, 12, 1024, 2048, 4096 is the 12 bits. So when we change a bit here, the 4096 is already taken up in the first 12 bits. So you have to do the per VLAN when you do the priorities. You have to change them in increments of 4096. So this would be 4, I think 4, 4, yeah, 4, 6, 24, 36, 38, carry 3, 4, 4s are 16. So this is divisible by 4096, and it's because of the way that it manipulates the binary numbers. These are figures that are in the book. These are the show spanning tree, and you can see these here, show spanning tree VLAN 1. What it says is this bridge is root, and this is on S1 on this thing. And when we go down here, it says that gig 1 and gig 2, which are going to be, these are going to be forwarding ports, because all of the ports are forwarding ports or active ports or designated ports. They're all going to be green on the root bridge when we do these things. It tells us designated, forward, and what the cost is. So if you can get to the show, it's going to tell you a lot of information. Hello time is 2 seconds. So what that means is it's sending the BPDUs every 2 seconds. And the one I was telling you about, the guy that they didn't want to use spanning tree, that's why they thought it was going to take up a lot of network bandwidth. It doesn't. And it really is not worth the risk. Spanning tree, show spanning tree. When we do these things, the hello time, the cost is 4. It gives us the priority, and this is again VLAN 1, 32769, which is going to be associated with VLAN 1. It's basically the same information that we had. Again, these are ones that are out of the book. Is entered is the bridge priority plus the VLAN ID. The bridge is placed in the lowest priority, the better the chance of becoming a root bridge. The priorities have the same that the MAC address is used to, like the root bridge, and I've said that a lot of different times. And this is, we're going back to show spanning tree VLAN priority 16384. This is the reason, the 12 bits here is the reason that it has to be in the 4096 increments, because that's what these will change it, because you're using the front 4 bits of this thing in order to do that. Stopping loops, we know that's what it wants to do. This is one that we calculated a little earlier. If we have failures, then we get into this thing, and it will, having witnessed it, it will bring a network to its knees, because there's no way to stop a broadcast, and what we get is a broadcast storm. And there's no way to stop a broadcast at layer 2. At layer 3, we have hop count, so it only goes so far until it dies. There's nothing to kill it at layer 2 except break the loop. PortFast is something, and what this shows is these are the one we're talking about. I said earlier, these are the trunk ports, and these are the ones that spanning tree is actually going to be looking to see if there's a loop, and if it is, we'll just pick one. It's going to block one of the ports. Access ports we have in units connected to, shouldn't have to worry about them creating loops, because there's just one of them. Now the issue becomes if Joe Schmo comes in here and plugs in his switch or his hub or his wireless or his whatever else, then he could actually create a loop. But we're going to have another one that's called BPDU. We're going to protect the BPDUs on this, so that when we put it the access, when we put it in access mode, and we enable PortFast, and we're going to do this so that if it gets a BPDU, it shuts down the port. And read his little story about being at his Super Bowl party and the guy that was doing it. What they were doing was something they weren't supposed to. They were plugging their computers into the core switch so that they could watch the Super Bowl. But they had the BPDU Protect enabled on these things. They plug them in and shut down the port. So the tech on duty calls him at his Super Bowl party and says that the core switch had died. They killed it by keep plugging stuff in and it shut down the ports. BPDU Guard is enabled, and when it is enabled, if we get a BPDU, somebody plugs a switch in, and we get a bridge protocol data unit, it's going to shut down the port. Now you've got to go back. Error disable is what it's called, but error disable means that it's disabling the port because of these things. PortFast, what we do is go to interface, and if you want to do it on more than one port, remember, if we do interface range, RA for range, FA 0/1/17, and then instead of say configure IF, it's going to say config RA. We can type spanning tree PortFast, and all of those ports will be put into PortFast so that you can connect things to them. The only ones, and then BPDU Guard, spanning tree BPDU Guard enabled, default puts it on all of the ports that are not truck ports. Or you can do a range or an individual interface with those things. Ether channel, and ether channel is Cisco's term. If we connected this up to the switch, what's going to happen if we did four of these things? And 3 of them are going to be blocked, right? On one or the other. Because we just created one enormous loop here. We can configure these things with ether channel, and there's 2 of them, the port aggregation protocol and the 802.3 LACP link aggregation protocol. Doesn't matter which one you use, they both do the same thing. What they do is tie all these things, all of these 4 together so that they look like a single connection. I'm not going to try to color the whole thing in, but a single connection. So if we had these 400 meg ports, 100 megabits per second, big B is bytes and little b is bits, by the way, when you write these things. What we actually wind up with is 400 megabit per second connection, full duplex, which really is 800 because we get 400 in each direction. So we can combine these things together. You can also do this on a Windows server with Windows, probably Server 2012 on up, probably before that. If the NICs support it, you can do that, and then you can combine it, put it multiples to a switch and get a faster speed, and that means that you can also send bigger windows through these things. If you do something that is non-Cisco, you've got to use LACP. If non-Cisco. If it's all Cisco, can't spell Cisco, can I? We can use the PAGP, port aggregation protocol. Aggregation would put them, we combine these things. When you do these things, the ether channel example, you can have 2 gigabits or 800 megabit ports connected together. So we do these, what we wind up here with is with a 2 gigabits per second. 2 gigabits, and so we have 2 1 gigs, we combine them into a single connection. The other thing is we don't have to block any of these things. If one of these goes down, ether channel, if there's only 2 of them, ether channel will automatically say, okay, I give up. I don't want to bind something that's not working. The other one will continue to work. So you take advantage of the looping of the duplication here. You don't create the loops. And they have you do one with the port channel, and I think the way the port costs do it actually makes that one go down. But those things, we can do those things. So ether channel, it's called port channeling. Combine 2 to 8 fast Ethernet or 2 gigabit ports. Ether channel is a Cisco term for port channeling, and port channeling is what everybody else uses. PAGP is the Cisco, and this is everybody else. If we have a Cisco and an everybody else, we have to use LACP. It's just like when you're connecting routers together. On the serial port, we use a Cisco proprietary protocol. If you connect it with anybody else, you have to use something that both of them use, because all of them are proprietary. The channel group command is used to add the interfaces to the ether channel. And then the interface port channel creates the bundled interface. But this is a way to have redundancy and use the things. You don't have to have blocked ports there. And that is the enhanced switch technologies. And I won't say all wrapped up, but I know it's pretty fast. All of it's pretty fast. But what we want to do is to be able to take advantage of the fact that we can loop these things, that if something goes wrong with a connection, we can use the most efficient one, and if something goes down, the switching mechanism will automatically keep the network up. Questions? Take a break and then maybe do it.